Steel and cast iron are the most widely used metal materials in modern industry, and their main elements are iron and carbon, also known as iron-carbon alloys. Iron-carbon alloys with different compositions have different structures and properties. If we want to understand the relationship between the composition, structure and properties of iron-carbon alloys, we must study the phase diagram of iron-carbon alloys. In iron-carbon alloys, due to the different interactions between iron and carbon in the solid state, solid solutions and metal compounds can be formed, and its basic phases are mainly composed of ferrite, austenite and cementite. The basic phases of iron-carbon alloys are ferrite, austenite and cementite. The interstitial solid solution formed by dissolving carbon in alpha Fe is called ferrite, denoted by F. This is the crystal structure and microstructure of ferrite, which maintains the body-centered cubic lattice of alpha Fe. The performance of ferrite at room temperature is similar to that of pure iron, with low strength and hardness, good plasticity and toughness, and it has ferromagnetic properties below 770 degrees Celsius. The interstitial solid solution formed by carbon dissolved in gamma Fe is called austenite, which is represented by A. This is the crystal structure and microstructure of austenite. And the austenite still maintains the face-centered cubic lattice of gamma Fe. Austenite has low strength and hardness, good plasticity and toughness, easy pressure processing, and no magnetism. Therefore, it is often heated to austenite state during forging and rolling to improve its plasticity. Cementite is an interstitial compound with a complex lattice, represented by Fe3C. Cementite has high hardness, extremely low strength, poor plasticity and toughness, and is very brittle. Cementite does not undergo allotropic transformation and has magnetic transformation. It has weak ferromagnetism below 230. Now what students see is the phase diagram of iron-carbon alloy, which is a diagram of the state or organization of iron-carbon alloys with different compositions at different temperatures under extremely slow heating or cooling under equilibrium conditions. The ordinate represents the temperature, and the abscissa represents the mass fraction of carbon. Any point on the abscissa represents an iron-carbon alloy of one composition. The state diagram is divided into several regions by some characteristic points and lines, which respectively indicate the phase composition of iron-carbon alloys with different compositions at different temperatures. The first is the characteristic point, point A. With a temperature of 1538 degrees Celsius and a Wc% of 0, is the melting point of pure iron. Point C, temperature 1148, Wc% 4.3%, eutectic point. Point D, 1227, Wc% 6.69%, melting point of cementite. Point E, 1148, Wc% 2.11%, the maximum solubility of carbon in austenite. Point G, 912, Wc% is 0, is the transformation point of pure iron allotropy. Point P, 727, Wc% 0.0218%, is the maximum solubility of carbon in ferrite. Point S, 727 degrees Celsius, Wc% 0.77, is an eutectoid point. Second, the characteristic line. The characteristic line of the iron-carbon alloy phase diagram is the connecting line of the transformation points of different composition alloys with the same meaning. ACD, which we call the liquidus line, means that the iron-carbon alloy of any composition is in a liquid state above this line. The liquid alloy is slowly cooled until the AC line begins to precipitate austenite, and the slow cooling until the CD line begins to precipitate cementite. AECF, called the solidus line, means that the liquid alloy is slowly cooled until the line is all crystallized into a solid phase, and the line begins to melt when heated. ECF is a eutectic wire. Any iron-carbon alloy with a Wc% greater than 2.11% will undergo eutectic reaction when slowly cooled to this wire. PSK is the eutectoid line, also known as the A1 line, which means that all iron-carbon alloys with a Wc% greater than 0.0218% will undergo eutectoid reaction and produce perlite when slowly cooled to this line. S-line, also known as ACM line, is the solid solution line of carbon in austenite. PQ line, the solid solution line of carbon in ferrite. GS line is also called A3 line, which means the iron-carbon alloy with Wc% less than 0.77%. The starting line of ferrite precipitation from austenite during slow cooling, or the ferrite transformation into austenite to the end line during slow heating. Phases. The iron-carbon alloy phase diagram is divided into 4 single-phase regions: liquid phase area, L; austenite phase area, A; ferrite phase area, F; cementite phase area, Fe3C. 5 two-phase regions. These two-phase regions exist between two adjacent single-phase regions, which are L plus A, L plus Fe3C, A plus F, A plus Fe3C, F plus Fe3C. In addition, the eutectic transition line ECF and the eutectoid transition line PSK can be regarded as special areas, where 3 phases coexist, respectively. Well, the iron-carbon alloy phase diagram is introduced here. Thank you for watching.